Hey everybody, Mr. Voppel here. As you can tell, I'm back in the bunker. Wherever you are, I hope you stay safe. Keep washing those hands. We're gonna make it through this, believe me. Well, I got an interesting problem that I wanna see if you can figure out, right? But the first thing you need to do is get your sheet that goes with this mission. Got it? See you soon. All right, everybody, feast your eyes on this. A normal lab cart? Think again. This lab cart is attached to a string. What's the string attached to? A pulley? And it leads to a weight? What? Oh my goodness. Well, hey, what about the other side? What? Another string attached to another pulley? Attached to another weight? Oh my goodness. What are we going to do here? We've got a cart with a string attached to each side with a weight hanging over the edge. So the first thing I want you to do is I want you to draw a free body diagram of this guy right here. But to do that, we got to understand about these guys. How do pulleys work? Well, here's our pulley right here. And you can see it's attached to this string. The string bends over the pulley. See, the pulley can spin, and it lets the string move back and forth, right? And so whatever is pulling on this string down here bends around the pulley, and it continues to pull on the string over here. Just like if I take this string and I pull on it, well, what's it attached to? The cart. So it pulls on the cart. What direction does it pull on the cart? Well, the direction of the string. So the string is this way. So when I pull on the string, it pulls the cart this way. So whatever is attached to this string, in this case this weight, the earth pulls on the weight. Gravity. It weighs something. And so the earth is pulling this weight down. The weight is pulling on the string bends around, it's pulling on the cart. And so what's happening is the force of the earth on this string right here is pulling on this cart right here. That's it. So now what I want you to do is I want you to draw a free body diagram of this cart. And what I can tell you is that on each side there's a 2 Newton weight hanging over the edge. So there's 2 newtons of force pulling on each string. And the other thing I can tell you is that this cart has a weight of 5 newtons. That's the force of gravity. So now your job is to draw a free body diagram like we've done before. I want you to draw all the arrows and label all the forces. So pause the video and go ahead and do that. Now that you've done that, I've got another question that I want to see if you can figure out. Okay, let's look at our first real-life example. So you can see right here I've got this cart. Like we said, it's got 2 strings attached to it, and this string over here has a 2 Newton weight attached, and on the other side is another 2 Newton weight. So 2 Newtons pulling this way and 2 Newtons pulling this way. And we can see this object is sitting here, right here. It's free to move. If I push it, just like normal, but it's sitting still. So the question is this object in equilibrium? Well, how would we know? Why don't you look at your facts, pause, and I want you to tell me, is this object in equilibrium? Yes, it's a straight line constant speed including an object at rest. An object at rest is in equilibrium, which means what about the forces? Are they balanced or unbalanced? They're balanced in all directions. In up and down, they're balanced, and left and right, they're balanced. Okay, so this object's in equilibrium. Well, let's see what happens when I take it, I'll move it over here, and I'm going to give it a push. I'm going to give it a push and release it so that it has some speed going this way. And I want you to tell me, is this object going to speed up when I push it? Is it going to slow down? Or is it going to move with constant speed? Okay, so I want you to pause the video before I do this. And I've got a motion detector here. So I'll set this up and I will use it to determine, we'll make a graph and we can look as a class and figure out is it moving with constant speed, speeding up, or slowing down. So pause the video and come up with an answer. Here we go. I got a velocity time graph. Remember, this is our Vernier app that we used. And you can see here, velocity is measured in meters per second here on the vertical axis. So whatever speed it's at is on the vertical axis. And above and below tells us the direction. That's right. And then here on the horizontal axis is time in seconds. And so what I'm going to do is I'm going to show you what happens when I hit play on this video and the velocity time graph we get. But before I do, I want to ask you, if the object is speeding up, and we know it's moving towards the detector or away from the detector, if it's going to move this way. It's moving towards the detector, yes, that makes sense. So my question is, if that's true, if it's speeding up, what would the graph look like? Now after I push it, remember, so it's going to speed up when I push it, but is it going to keep speeding up? Well, if it's going to keep speeding up, we would see it would start to speed up and it would get further and further and further away, right, from the 0. It would get further from that. If it was going to slow down, right, so I push it, I speed it up, what would it look like if it was going to slow down towards the detector? Well, it would get back closer to 0, right? Yeah, it would go back down to 0. And if it was going to move with constant speed, what would we expect to see? Well, remember, when I push it with my hand, it's going to speed up, right? Now, if it moves with constant speed, what's the line going to look like? It's going to be flat, like this, until we stop it, right? And then it would slow back down. So now the question is, what's this graph actually going to look like when I hit the video? Oh, it was constant speed. Look at this. This line is flat. Look at that. Just like we expected when I pushed it, it sped up, right? Sped up when I pushed it. But then after that, when it was moving towards the detector, it had constant speed the whole time. The graph did not keep going away from the horizontal axis, which would be speeding up faster and faster towards the detector. No, and it didn't go back towards the horizontal axis. The graph did not get closer to a speed of 0, which would be slowing down. No, it kept going at a constant speed there. It kept at the same speed until it hit the detector and it slowed down once it hit the detector and came to a rest. And so what we know is the object moved with constant speed. And that makes sense. While the cart was moving right there with nothing touching it except the weights on either side attached to the strings, it was in equilibrium. It was in equilibrium while it was right there, while it was moving along the track. And what that means is the forces are balanced in all directions. So yes, we had 2 newtons pulling this way from that weight that was hanging over the edge. And yes, we had 2 newtons pulling this way from that weight hanging over the edge. And we also had the force of the earth. This cart weighs 5 newtons, so 5 newtons pulling down, which was balanced with the force of the table pushing up, which was also 5 newtons because it was in equilibrium. And so what we know is that while the cart was moving here, the forces are balanced in all directions. And because of that, it moves in a straight line at a constant speed because it's in equilibrium. So there you have it, your first real case of an object in equilibrium. The forces are balanced in all directions.
Left and right are balanced. Up and down are balanced. And so what happens is the cart moves in a straight line at a constant speed or remains at rest. There it is, it's remaining at rest. Or after I push it, it moves in a straight line at a constant speed because the forces are balanced, equilibrium.